Now we're going to look at how we can compute a t-test using two samples and without knowing the values for the standard deviations of each population. So with this, we're going to go into the calculator and we are going to go into our two-sample t-test computation in the tests menu, option 4. And for this, we need to pay attention to a couple of important things as we're putting our values in, which, by the way, we have stats, not data here. We have the mean, standard deviation, and sample size for each of the two data sets. We have the assumption of normality to make sure that we can actually do this. And we also assume that we don't have equal variances. That assumption is very important with what goes on in one particular entry in the calculator, and it messes with a whole bunch of formulas that we're letting the calculator do the hard work on. But anyway, what we're going to do is put in our data, so 473 for x bar 1, 39.7 for x bar 2, 8 for n1, and then 459, 24.5, and 18 for the second data set, where we are testing for any difference, and as a result, we're going to pick the not equals option. This is the easiest one to work with because there's a little bit of an arbitrary side to the other two, but I'll talk about that in a second. Anyway, here, because we're assuming the variances are not equal, we are going to select the non-pooled option, so no for that, and then we can calculate. Where what we're going to get is, in this case, a t-score of about 0.922, along with a p-value of about 38%. So if you want to think about this in terms of p-values, we would fail to reject the null hypothesis as p is, well, significantly greater than alpha. If we want to use this with a critical value test, well, we'd need the critical value, and for that, since we have two tails and where are you? Alpha equals 10%, we're going to use inverse t with 0.95, because we're just going to get the upper value here. And since we don't have equal variances, we pick the smaller one. df is 7 in this case. You may have noticed that if you're looking at that in the calculator and the output, you get something for the df from there. That's using a very different computation, and we're not going to worry too much about. Anyway, you have this, and as a result, we can get a t-score to compare of 1.895 and negative 1.895. Those are our two ends, and our test statistic is well between both of them. So for this reason, we would fail to reject, much like with the p-value. For another example here, where we're looking at these costs per mile with two types of cars, we are trying to see if one is less than the other, where we are assuming equal population variances, which means we're going to have a slightly different input, and also there are going to be some different formulas going on in the background, and, well, you should be happy to use the calculator instead of dealing with these. So anyway, we're going to go back up here, and we're going to put in a lot of the same sort of things as we did in that first example. Stat, test, two-sample t-test, using stats. So we have 0.48, 0.05, 30, 0.51, 0.07, and 32, where from here we're looking for the manufacturer to be smaller than the competitor. For this, we're going to take the left-tailed test, but understand that that's kind of arbitrary up to the fact that I put the manufacturer information in as data set 1. If I flop these two, I'd look for a right tail and have almost exactly the same meaning. So don't be thrown off by that, but it is a little arbitrary. Anyway, we pick the left tail for this, and because we're assuming equal variances, we will say these data sets are pooled, calculate, and we get, among other things, our t-score here of negative 1.93 and a p-value of about 3%, where that p-value of 3% is less than alpha equals 5%, so we could we would reject the null hypothesis. And similarly, if you want to do this with the critical value approach instead, we would go back up to here, understand that because these things are pooled, when we're putting it in to the inverse t function, we will have 60 degrees of freedom. Oh, not the area. I'm a little ahead of myself. I need to put this in first, where the alpha is 0.05, and 60 or 30 plus 32 minus 2 degrees of freedom. It's a very picky computation, but the result here is we get about negative 1.671 as our critical value, and we can see that the statistic we get here is to its left. And because it's to its left, we reject.